Hello.
Hello, Dr. Kedar. Welcome.
Good morning, sir.
Yeah, it might be very,
It's dark.
dark in the Scotland. Okay, yeah. So, very good morning. We will start the session. Over to you, organizing team.
Yes, sir. Good morning, one and all, and welcome back to the second session for today. It's a great honor for me to introduce you all to our eminent speaker for this session, Dr. Kedarnath Rane, who will be taking this session on extrusion based additive manufacturing. He has been lead research and development engineer at National Manufacturing Institute, Scotland, with 8+ years of experience in advanced materials and power based manufacturing processes. He has been continuously involved in cross-functional groups constituting of scientists, engineers in both academia and manufacturing industries for encouraging sustainability and mass customization in the Industry 4.0 scenario. While working on the challenges pertaining to metal powders, 3D printing, process monitoring, topology optimization, and net shape manufacturing, he has gained diverse skills which include competence in manufacturing processes such as additive manufacturing, metal forming, powder metallurgy, and metal injection molding, etc. Over to you, sir.
Thank you very much for kind of very brief and kind of versatile kind of introduction. So today we are going to talk about again additive manufacturing, but particularly as you see in that profile, it is related to the powders and powder-based additive manufacturing processes. So let me share my screen first. Can you confirm that you can see my screen now? Hello.
Yes, yes, it is visible and you are quite well audible as well. You can go ahead.
Okay. Thank you very much, Bode sir. So again, again, thanks to Professor Bode for inviting me here to talk to you all today, as we are looking at various additive manufacturing 3D printing processes through this FDP program. The topic I am covering today is extrusion-based additive manufacturing process, particularly for metals and ceramics. As we know that the common terminology 3D printing is very much applicable for polymers or plastics, but the same kind of extrusion-based system can be implemented for metals and ceramic powders. I am currently not working in this domain because I am currently involved in other kind of aspects of manufacturing, particularly digitization and sustainability. But this is based on my past experience and my past research work. Today, I am going to cover, uh, first of all, we can start with extrusion-based additive manufacturing process, a brief introduction to the process, how it works, and what are the major steps, because this is not a single step process, it's a multi-step process, and that is one of the limitation of this process. But there are some merits as well that we will going to see through this presentation. Then, before introducing to the extrusion-based additive manufacturing, we need to see enabling technology, which can make this layer-by-layer manufacturing of metal and ceramic possible. And that's why we are going to cover metal injection molding and powder injection molding. Many of you are not aware about this kind of process because it is not in the mainstream of mechanical engineering or manufacturing engineering. So we will touch upon this kind of very specific kind of processes. Then we are going to cover about like in brief about the extruders which are used for extrusion based additive manufacturing. Then we are covering all the process aspects of the process. Then we can see how machines are developed and available in the market for this technology. In latter part of the presentation, I will talk about my work related to extrusion-based additive manufacturing and current ongoing work related to this technology, because you know that additive manufacturing is still evolving and there is a lot of things to do and it is happening very quickly, right? So we can see if there any opportunity for you all engineers and professors to work on this domain. Then we are going to cover kind of very kind of attractive merits of the process as compared to conventional additive manufacturing process. Particularly, I am kind of comparing with powder bed based processes like SLM, EBM. They are much mature process, I must believe. So we are going to cover some kind of comparison points over these kind of processes. And at the end, I am summarizing the presentation and open for some questions and discussion points. Let's start with the extrusion-based process. What is basically novel in this process is that we are using the material which is in the semi-solid or liquid form to be deposited. So we are using kind of nozzle or orifice kind of system to deposit the material in semi-solid form. Here you may have question that how you can melt metal or ceramic. Ceramic is having some typical ceramic like alumina 2700. So we are not going to melt it at 2700 degrees Celsius, but we are using some kind of system to get it deposited. We can cover this aspect today's presentation. There are kind of some commercial names available for this kind of machine. For example, few machine provider called it as fused filament fabrication, FFF. Then you can also learn from many kind of commercial websites that it is called as fused deposition modeling or FDM. So Stratasys patented this technology long back and now it is open for everyone to use. But again, previously it was only used for polymers. Now it is also like last few years, we are developing a lot of integration technologies where we are using this kind of method to deposit metals and ceramic as well. Like in late 90s, there are some attempts in few universities to deposit such kind of material, and they called it as robocasting. But again, it is very old technology, and they are not used in recent years. So we are aware about some of the technologies which are used in the past, but we are jumping to the new technology which is called as EAM for metals and ceramics. So it is a schematic that I took from my review paper. So it is related to the brief introduction of the process steps, where we are starting with the feedstock preparation. The feedstock is the mixture of metal powders and polymers and non-metallic constituents to get it extruded or deposited. So we will cover some of this aspect in the coming slides. So then once it is ready in the form of pellets or wires or filaments, then you can use it for the deposition process, which is again similar, you can say similar to the conventional 3D printing, but there are many variants of machines available nowadays. So we are going to see various variations of this machine itself. Then once it is ready with the deposited 3D geometry, we need to use kind of post-processing. You can not say a complete post-processing. Before post-processing, there are a couple of stages to remove the non-metallic constituents, because we called the process as metal and ceramic, right? So we need to use some kind of process like debinding to remove the non-metallic constituents, sintering to remove the voids in the part so that it get consolidated as a solid part. So now I'm talking a kind of a brief introduction to this EAM process, but as I told you in the kind of outline slide where we are using these kind of steps which are derived from a process called as powder injection molding or metal injection molding. So we, before jumping to this process, we need to look at some kind of fundamentals behind these process steps. Okay, so excluding this deposition step, all other steps are common in the metal injection molding and powder injection molding process. So let's see how it works. It starts with the powder mixing. So you can, if you have one base material like iron and some alloying element, you need to put it together. You need to mix them in dry condition. So when alloy is ready, alloyed powder is ready, you can transfer this powder to another mixing unit where you are going to mix it with non-metallic constituents like polymer and wax. Many times it is not termed as an eco-friendly kind of system, but nowadays you can see there are some water soluble binders are also available. So we can see this process again like kind of gluing of powder with other non-metallic constituents, so that it is a kind of viscous and in the form of some semi-solid form. Once it is ready, we are going to use it for a kind of next process, which is here for metal injection molding. It is called as injection molding. It is similar to the plastic injection molding, but design aspects of the tools and pressure requirement for this kind of molding is different. So you have cavity mold, and like you can even develop family molds, like multiple parts at the same time with this process. So you are going to charge the material here in the hopper. So molds are getting closed. You are putting the material in the hopper. Again, because of the non-metallic constituent polymers, it is easy to melt this kind of feedstock. So it is getting melted through the kind of stage-wise manner, and you are going to feed it here to this kind of cavity. The material is injected to the cavity now, and you can see it is fully injected, and there is a cooling happening. Like once it is solidified, you can move it the material like the part out. Likewise, you can continue with multiple kind of parts production, like similar to the powder injection molding or metal injection molding. We can use similar concept, which is debinding and sintering for the post-processing of EM parts, where we put this part. But again, I think in this schematic, they are skipping the debinding step. We are going to cover it in later slides. So they put it this kind of part for removing the non-metallic constituents. So they are showing a kind of powder bed, a kind of bed type of pusher bed furnace. During the debinding, non-metallic constituents are removed. Some of them are there, but again they are vaporized during the sintering process. So it is sintering is basically we are hitting at around 0.7 times of melting point of the material. So it is getting kind of diffusion bonding happening during the sintering process. The particles are coming closer to each other, and you get a dense part out of the furnace. So here we are going to take the part out, so it is getting cooled. If there is a post-processing required, you can do post-processing, or you can use the part as it is for our needs. This is about the process steps and a brief kind of animation for your introduction. When it comes to the capability of the process, as you can see, it is similar to the polymer or plastic injection molding. You can make very high level of complexity through this kind of process. You can see in the left side, it is mentioned that during the sintering, the part is going to shrink between 12 to 18%. It is just because you have the kind of constituent which are like polymers or wax, which is getting vaporized or evaporated during debinding step, and you get solidified parts later stages. Then when it comes to application domains, you can see it is applicable to various domains like defense. You can see complicated parts manufactured. Then you can see even at a micro scale how neat and clean parts are produced. So you cannot expect any kind of post processing required for such kind of parts. Again, the metallic finish as well as the surface quality, it is depending upon the kind of pressure requirement that you are using for the process, as well as the kind of particle size that you are using for this kind of process. You can get very high surface finish using this process. Let's see which are the kind of typical material processed through this technology. In terms of metals, you can see the list is enormous. You can see all kind of metals which are available in the form of powders, which we can process it for using metal injection molding or powder injection molding. Even tool steel, high melting point metals are covered in this list. When it comes to the ceramics and carbides, again, list is almost complete here. Whichever is possible ceramic in the form of powders, we can cover it for this process. Considering the high melting point of ceramics and carbides, we required a kind of substantially higher sintering temperature as compared to the metals, because most of the metals you can see they are having melting point in between like 700 to 1300 for most of the common metals. But for ceramic, we are going for temperature like from 1300 to even 1800 degrees Celsius. So this is a kind of distinction of the melting point involved. But anyway, we can use any material to process through PIM technology. When it comes to the metal powders required for the additive manufacturing process, I would like to cover all additive manufacturing process so that you can get distinctions where the metal injection molding powder size lies for the requirement. Here we are aware about some of the processes, which is direct energy deposition, okay, like LMD and PMD. We required a kind of higher side of particle size because the powder is getting, I think tomorrow you are going to cover this kind of deposition process for this kind of DED processes. So you will have more insight to this kind of powder sizes through tomorrow's lecture. But when it comes to other processes like laser powder bed fusion or electron beam powder bed fusion, we are using a kind of powder size which is less than 60 microns. For HIP, it is a complete different application and different process we are not going to cover. But when it comes to the metal injection molding, we are very much specific. We have very much specific powder particle size, even though it is saying that around 30 micron size is possible, but it is a range of powder. But I must recommend that 0 to 20 micron is the best powder particle size for metal injection molding and powder injection molding. When it comes to the metal, you can get this powder particle size easily. But when it comes to the manufacturing process, powder manufacturing process for ceramic, 20 micron particle size is even difficult. So we are in the domain of powder injection molding where particle size is favorable from 0 to 5 microns. That is a kind of favorable particle size for powders of ceramics. When it comes to the use of the powder for various aspects, like various application, you can see diverse processes are aligned On y-axis you have powder like part size in kilograms, and on x-axis you have powder production volume, okay, in thousands and millions of parts. When it comes to the use of metal injection molding, you need to consider the cost for post processing as well as the tooling cost, which is because the tooling is like injection molding, and in plastic injection molding we are going to produce millions of the parts. Similar to that, metal injection molding, we are considering the process viable, suitable for parts which are required in thousands, okay, all the time. Unlike other processes like laser powder bed deposition or LMD or heap and others. So this is one of the kind of drawback of this process, because it is not suitable for lower volume production. That's why we are considering extrusion based additive manufacturing as a kind of technology which is competing with other available additive manufacturing processes, considering the complexity and the cost of the process. When it comes to the powder particle size, we required very good flowability of the powder, because flowability means it is, although it is the powder is the material is deposited in the cavities by virtue of polymers, but flowability in terms of the shape of the powder, the packing density during the sintering, the level of contamination are important factors to cover. Again, when it comes to the part level, the green strength, which is because that after injection molding, the part should be handled carefully because it's fragile, because it is not sintered, right? So green strength is also important. Porosity, the level of porosity at the later stages, sintering strength, and mechanical properties, they are the important aspects to consider during the metal injection molding process. When it comes, again, I'm spending more time on powder injection molding, because as it is an enabling technology, all the aspects related to the powder injection molding is equally employed for extrusion based additive manufacturing. That's why we are giving more stress on this process. When it comes to the manufacturing of powders, as you are maybe aware that there are multiple processes, like through kind of chemical treatments you can produce powders, like usually in the form of like oxide or plates or something. Electrodeposition is another process. Atomization of powders is one kind of mature process for the production of spherical shaped powder. Here you can see water atomization process, where kind of typically steels and other kind of metals, this process is very much viable. When you come to the kind of shape of the powder, you can see here comparison, the sponge iron powder, which is produced through kind of reduction technology. I'm not covering to the metallurgy side of this kind of processes, but it is in a kind of irregular shape. When it comes to the atomized powder using water or a gas, it is much spherical in size. So this is a kind of distinction of powder sizes. When it comes to the diversity of the manufacturer, you can see BASF, Hoganas, Sandvik Osprey. There are n number of powder manufacturers which are producing the powders for various applications. Here we are seeing three different type of powders which are produced from carbonyl process. So you can see very specific, very kind of spherical powders. When it is gas atomized, you can see there is a kind of bimodal particle distribution. One is bigger particle and another are smaller particles. Then third category is water atomized powder, which are, again, you can see some kind of agglomeration is there because of the process itself, which is 17 pH steel powder. When it comes to the comparison of small particle production technologies, we can see each process is capable of producing powders, but the size of the powders and the mean size is different through each powder. The shape is different, and the processing technology is suitable for different material combination. For example, carbonyl process is only suitable for pure metals. So alloying kind of thing is not favorable for carbonyl process. So I'm taking this kind of details from some books which is given here. Okay, so if you want to refer to more kind of information, please go to this kind of reference, and you can read more on this kind of technologies or powder requirements. When it comes to the desired powder particle characteristics for this kind of application, here we are seeing a typical distribution of particle size for metal injection molding powder. Inconel, again, it is one of the specific requirement. Inconel 6 to 5 gas atomized powder. You can see the mean particle size is here. You can see, like, let me tell you here what is mean by D10, D50, D90. So D10 means is that you know that there is a distribution of normal distribution of the any kind of samples. So it is 10% of the powders are in the domain of 5.7 micron size. So you can see it's a kind of mean particle size. Okay. Again, D50, again it is a mean particle size, but covering 50% of the powder volume. It is 12 microns. And when you cover 90% of the powders, it is 23 microns. But usually when in general, when we say like mean particle size, we usually take D50, like 12.86 micron is a kind of mean particle size we can consider suitable for MIM application for Inconel kind of material. When it comes to some characteristics, again, they are listed here. We have a tailored powder distribution required for improved packing. So like bimodal particle size is favorable because the kind of interstitial spaces which are vacant during the from the bigger particles, they are covered through the smaller particle size. But again, it is having some kind of cons, which is flowability, which is influenced through this kind of distribution. There should not be any agglomeration or kind of clustering in the powders. So like powder manufacturer takes care of this kind of aspect. Spherical, as I said earlier, spherical powder particle size is favorable. Equiax powder shapes are favorable. Next aspect is like when we want to consider the kind of bound post processing or the post steps in the process, we need to consider a powder particle size which should facilitate binder removal. Like it should pass easily in between two powder particles. So that is another aspect we need to consider for selection of the powder. Typical powder particle size is around, as you can see, around 10 to 15 microns, which is favorable. No internal voids, minimum exposure, like explosion and toxic hazard. Again, when it comes to the powder manufacturing, if you remember that manufacturing of kind of aluminum or magnesium kind of powders and handling them, it is very dangerous because it is a kind of as you go smaller and smaller, the activation energy for explosion is very high. So that's why we cannot go very small particle size. And some typical materials are very hazardous as well, like cobalt, like molybdenum. This kind of toxic hazardous material should be handled carefully. When it comes to the particle interface and interaction with the binder, it should be very clean and there should not be any residues, because it's again about the surface characteristics of the powder. Again, spherical particle size with smooth surface is favorable for this process. These are the typical powder characteristics we required for such kind of processes. I know it is a bit kind of specific, but that is what we required for this kind of processes. When it comes to the binder, which is kind of required constituent for PIM as well as EAM process, we categorize them into the three kind of categories. Because there are n number of binders available, there are a lot of research on pros and cons of each binder, but here it is just a brief. There are three categories of binders available, which is thermoplastic, then again polyamide or polymethylene kind of. So again, this kind of binder system require a special debinding system, which we can see in later slide. Then kind of polyethylene glycol or gelatin based binder, which is soluble in water. Okay, so these are the three basic categories of polymers required for these processes. And you can see polymer backbone polymers suitable, because one is a kind of wax component and another is a kind of backbone component of the binder system. Most of them are available commercially. Similar to that you have glycerine or boric acid kind of binder suitable for this kind of application are also available commercially, and they are termed as eco-friendly kind of binder system. Additives and surfactants are important. As we see in the previous slide, the surface contact between the powder and binder should be smooth. They can facilitate the movement of the feedstock easily, as well as the removal of the binder during debinding process. That's why we need some additives for the process. So they are listed here. When it comes to the chemical composition or the chemical structure of some of the binders, they are listed. I'm not going into details how they look like and how they are facilitating the process, but it is worth to mention that the kind of complicated polymeric chains are not advisable for binder formulation, because they take efforts to remove them during the debinding and thermal debinding process. So simple like polyethylene, like for example PEG or PE or PP kind of polymeric system, they are favorable for this kind of applications. Again, when it comes to this kind of system, you need to choose a special kind of debinding system for different kind of polymers that we can see in coming slides. Once you have ready with polymers as well as metal powders, we need to mix it as per the previous animation. We can use like in the animation itself, we see some kind of Z blade mixers are used, which are rotating, and heaters are around these blades, so that the powder and binder system is in the semi-solid form, and they are churning it together so that they are getting homogenized, mixed together. A very high distribution of powders within the matrix of polymer binder is taking place through this kind of mixture. In kind of commercial production or a continuous production system, they use shear rolls for deposition for mixing such kind of powders. So you use again continuous process to mix the powder for mass production. Again, typical there are kind of very specific companies which manufacture this kind of feedstock. So you can research on this kind of aspect. Who is manufacturing? One of the big player is BASF. Okay, to get this kind of feedstock ready. But you can anyway use your own Z blade mixer to manufacture a kind of customized powder. Feedstock. When it comes to the kind of physics of mixing, you have on y-axis mixing torque, on x-axis powder volume loading. You can see it is very evident that as soon as you increase the powder volume, like the kind of solid loading in the polymer, you required higher torque, like higher efforts to get it mixed. But again, when we say that very high powder loading is also not beneficial. Very low powder loading is not beneficial. Why? Because very low powder loading means you have very high volume of polymers or non-metallic constituents, which in later steps result in very high level of shrinkage or even distortion in the part. Very high level of powder loading is also not favorable because of the torque requirement itself, the energy which we are using for the mixing. Plus, it is also not favorable because very high powder loading means lower flowability of the material, because you have very low polymers to flow the material. So very complicated shapes cannot be manufactured. So you can see here the zone 2, which is saying powder volume loading in terms of 62 to 70% is favorable for this process. Okay. Similarly, as you can see, with respect to time, your torque is going to increase because of the kind of quality of the process, as well as the powder loading is considered. When it comes to the micrographs of different volume loadings of the powder, you can see again it is in so many times that at a scientific level you can term it as volume loading, but when it comes as a kind of shop floor level, people use weighing balance to measure this kind of powders, and they usually use in weight powder loading by weight. So instead of 62 to 70, the powder loading in terms of weight, it may result from 85 to 93% by weight. Okay, but again, when you say 90% powder loading by volume, it is around 65. Okay, because the density of polymers and density of metals are different, right? So that's why there is a difference between volume loading and solid loading by weight. You can see here when it comes to 60%, you have lot of polymers deposited and surrounded by the metal powders. Again, it is favorable in terms of flowability, but not favorable in terms of sinterability of the process. 66% it is okay. In between, we can say it is a kind of optimal composition of binder and metal powder. 72%, you can see there are very few polymeric constituents, and it is very difficult to injection mold or even deposit. Plus kind of sintering as well. When it comes to the feedstock, so like once you have mixed the powder, we go for manufacturing of feedstock. So feedstock is in the form of kind of granules, but as a commercial purpose, people use it another step called as extrusion, and then there is a pelletizing unit is fitted in the machine, where you can get such kind of pellets from metal feedstock and such kind of pellets from ceramic feedstock. It depends on the kind of system that you are employing here for cutting operation. When it comes to kind of commercial, another kind of binder system, catamold. I'm not going into the more detail of what are the commercial systems and all, but they have different shapes. Like alumina, PEG based system, you can see different shapes of feedstock granules. So you have different variety of feedstock available commercially as well. So you can buy it directly from the supplier and use it for injection molding or EAM process. When it comes to the feedstock properties, again, we need to test the properties of different constituents at different levels, at different process steps. Here we consider viscosity because it is in the semi-solid form. During the injection molding, we call it as rheological characteristics. Again, if you are not aware about this terminology, it is nothing but the kind of flowability at certain temperatures. We call it as rheology. So we are changing shear rate here on x-axis, and apparently you have changes in the viscosity on y-axis for different temperatures and different composition of feedstock. And you can see if you have lower temperature, you have higher viscosity. If you have higher temperature, you have lower viscosity. Again, shear, when you see on the x-axis, higher shear rate means very low viscosity, again favorable. So it is a typical shear thinning behavior. All polymers and feedstocks are showing through this kind of mechanism, flow mechanism. Similarly, for different composition and different mixtures, you have there is a shear thinning behavior again. Higher shear rate, lower viscosity is a typical behavior. So we can see this kind of behavior similarly for EM applications as well. Once you are tested with feedstock properties at certain flow rates or certain shear rate, again, shear rate is depending upon, like you can please note down the shear rate that we are considering here for powder injection molding. Okay, and when we can see extrusion based process, it is completely different. So it is more kind of lower domain, and that's why it's challenging to get it deposited. But for molding application, you use very high shear rate. It is very easy to be deposited. A typical kind of machine, arbor press or injection molding machine is used to manufacture such kind of complicated shapes. You can see the part is looking very bulky, like 500 to 600 grams size of the part is manufactured within seconds through this machine. So that is the merit of this process. Like you can make very high complicated parts within few minutes. Okay, but again, you have post processing. But when it comes to post processing, we can process the parts in batches. So that's why the productivity is very high through this kind of process. Once you are ready with this kind of molded products, you can go for debinding process. Debinding is differentiated into the three categories. One is solvent debinding, thermal debinding, and catalytic decomposition. As I said earlier, POM based kind of system required a kind of specific catalytic decomposition mechanism to process the parts. But for most of the MIM and PIM system, these two components are kind of regular. One is solvent debinding, where you are removing a kind of soluble constituents from the binder system. And again, this is not a kind of typically melting of the binder, but it is basically a kind of diffusion based system where you are it is similar to a deposition, like melting of salt in water. It is similar to that. You can either use water or some kind of petrochemical liquid to deposit the binder constituents, and therefore it is very easy to handle such kind of parts. But again, when it is getting solvent debinded, we called it as solvent debound part. They are very, very fragile. The handling is a challenge through this process. The next process is thermal debinding. As we see earlier, there is a binder constituent which is called as backbone binder. We need to remove this binder system again before sintering process, and this solvent debounded part goes to the furnace. Again, it is not very high temperature. The furnace uses vacuum or some kind of reducing gas to process debinding process. Here you remove all the binder constituents which are present in the part. So again, many people call this process as not eco-friendly because you are vaporizing the polymeric constituents, and they are getting but there are some filters, there are some chambers which can condense the kind of vapors of this kind of thing. But there is a lot of research going on to make it more greener. When it comes to catalytic decomposition, they use some kind of acids because it's a typical polymer to get it removed from the part, and you need to remove it in a quick succession because it's a nitric acid, And there is some another system called as supercritical CO2. I'm not going into details of this system, but to make it the process commercially applicable, there are a lot of things are going on to improve the process characteristics. How the process work, it is showing in the schematic. You can see this is a kind of metal powder, and yellow and kind of other color is representing the binder, which is getting removed during the debinding steps. Like backbone binder is there, some solvent is there, then solvent is removed, then you can remove the particle. Again, in this picture, you want to consider that to understand the melting of the polymer, you can go for TGA analysis. You do it TGA, and you can have kind of clear picture how much time it takes to remove the complete binder at different temperature conditions, like PP, paraffin wax, stearic acid. Different binder constituents require different kind of hold time and temperature to remove the constituents. When it comes to the efficiency of the powder debinding process, it is again depending upon on x-axis you have time. So as soon as you go on increasing the time, your debinding process is getting completed easily. But again, this is one kind of bottleneck for this process. If you go for very high complicated shapes and very bulky shapes, you require very even 24 hours of the time to remove the binder constituents. I remember there are some parts I processed. It even took 48 hours to remove the complete binder constituents. But again, this can be happened in batches, right? So it will not influence productivity that much. When it comes to the thermal debinding process, we need to design a kind of stage-wise cycle to remove the binder constituents completely. You have different kind of constituents are here. Like they are either in the interstitial spaces or in between there is a kind of agglomerate of this kind of binder system. You need different kind of hold times to remove this kind of binder system. So it is typically at lower temperature as compared to the sintering temperature, as you can see here. And to avoid kind of damages or defects in the part, you can see you need very slow heating as well as cooling during the debinding. So many times it is processed in different furnaces. That's why I termed as cooling. But if it is integrated process, debinding and sintering, you can have only heating process. So you can see this is a kind of typical heating rate which we need to consider for removing of all the binder constituents without any kind of defects. If you go very high heating rate, you will have slumps or defects or cracks. If you go very slow, the productivity is very low. So that's why we need to follow this kind of route to design the heating system for thermal debinding of the parts. By the way, Randall German and Animesh Bose, they published a very good book on this kind of process. If you are more interested to in this process, please go and visit. It is a kind of most cited book in this technology. When it comes to the sintering process, again, we have continuous debinding and sintering furnace for continuous production of such kind of products in mass quantities. Whereas if you want to go for the batch production, you can use such kind of furnace, which is a kind of, there is a chamber, you can close it and you can do thermal debinding and sintering in one station. But here you have kind of pusher bed kind of system. As you can see, we saw in the schematic, there is a debinding station, there is a sintering station involved in this kind of system. So that is about the kind of sintering process. The mechanism involved, again, I already covered briefly the mechanism. You have powders. Powder is bounded together very close. but there are voids in between. During sintering, the powder particles comes together, there is a diffusion bonding is happening, and you can see you will have very low porosity after sintering. You can compare from here to here. It is like dense. You can get a very high density up to 99.5% through this process. And typical microstructure after sintering looks like this. On the right side, you can see 17.4 PS steel sintered at 1300 degrees Celsius with some tempering post-processing. You can see some kind of phases, some microscopic phases involved in this kind of operation, and which is suitable for defense applications. Again, another steel very common, stainless steel 316L. You can see kind of austenite and some twins and some phases involved, and it is very suitable for biomedical application as well as some kind of aesthetic application and some kind of application where corrosion resistance is involved. So we can use this kind of material, and you can see there is no porosity in the sintered microstructure. That means the sintering is very good through this kind of process. Unlike other additive manufacturing processes, you have a lot many pores, right? When it comes to the process optimization for debinding process, sintering process, we have density considered here, and with respect to time, we can see there is a increase in density when you consider accepted parts. So there is a kind of typical density like 95 above is a suitable density for any application, any applications where metals and ceramic are considered. So you can see you required almost more than 90 minutes to process parts, or even 2 hours. Like when it comes this x-axis as a time, it is the dwell time, not the complete cycle time. This is the green density and this is the sintered density. So green density is around 55 to 60%. Why? Because as you see in our volumetric mixing kind of thing, we are considering volumetric loading optimum at this point, right? So other constituents are non-metallic constituents, typically binders, polymers are involved. That's why the green density is low as compared to the sintered density. When it consider a kind of apparent kind of characteristics of the parts, the warpage in the part is observed when you consider different kind of bad kind of characteristics of the part during different kind of support system. Density is always high when you consider kind of beads kind of thing, but again dense surfaces on the surface characteristics, it's always favorable because of the process itself. When it comes to the mechanical properties, I know that I am spending a lot of time on considering metal injection molding, but it is equally applicable for powder extrusion based additive manufacturing. That's why we need to cover these aspects. Okay, so density, and again UTS, we can see there is a increasing or the kind of linearly increasing trend. As soon as you increase the density, your strength is going to increase. It is applicable for any kind of combination of heat treatment or any material. When it comes to the fatigue life, because some of the parts are going for higher fatigue life, like higher fatigue application, you can see as soon as you increase the kind of different kind of composition, you will have different kind of fatigue life. Again, this kind of fatigue life is correlated with the density. You have higher density, you have higher fatigue life. again, porosity density is the same, is the inverse of density, right? So we are considering in this plot porosity on x-axis, and in the percentage what is the different characteristics of the parts. If you increase the porosity level, your weight is going to reduce. It is the kind of physical characteristics. But when it comes to the mechanical characteristics, you can see it is like significantly reduced. The UTS, same, it is applicable for yield strength, RM, A and IE, which is related to the kind of elongation and impact strength of the material. It is getting very highly influenced through the porosity. Here you can see the elongation, which is kind of important for some application. If you reduce the porosity from like 0% to 10%, it reduced significantly. Like it is almost reduced by 30%. Like it is only 30% when you reduce 10% of porosity. The same applicable for impact strength. The impact strength is very important characteristic, some kind of defense applications typically, where there is a blast loading is there. So it is very important to consider the porosity level. So that's why I said typically 98-99% porosity is favorable. 98 to 99% density is important for many applications. When it comes to the use of MIM and PIM process, relatively growth is there. On x-axis you can see low and high. Although the process is very much mature for jewelry and some kind of aesthetic application, instrumentation, very complicated system, it is equally appreciated for aerospace, electronic packaging, medical and telecom industries. But again, when we consider this kind of application, as the process is very much mature, that's why we can as a kind of very high level of data is available, that's why we can distinguish the applicability of this kind of processes. But when it comes to the AM, additive manufacturing, it is not so much mature process that we cannot distinguish which is the area is favorable for each processes. It is yet to come. When it comes to the applicability of PIM or MIM process, you required so like when a typical manufacturing engineer select a metal injection molding process suitable for production of certain shapes and quantities, you can see this kind of down selection criteria. You need to consider very high quantity requirement, like typically in millions of the parts, very high geometrical complexity, very high geometrical precision required. Size of the part is again it is in between some millimeters to some like in microns, like 1.5 millimeter, maybe it is a higher dimension. But as we saw in the previous pictures, micro injection molding is also very important factors typically for telecom and electronic applications. And material, so material I should not consider as a down selection criteria, because most of the material available in the powder form can be sintered, and it is possible in MIM. But major bottleneck to apply this process is quantity, okay, and size. So considering this limitation, we must say that today's era of mass customization as well as kind of versatile or kind of flexible manufacturing approach, we cannot use this kind of PIM process for producing parts for various applications. Typically biomedical, where mass customization is coming, aerospace applications where bigger shapes are important, are appreciated, defense applications where kind of there is a customization again coming to picture. There are some kind of requirements where this PIM is not suited for the requirements. So how to tackle this problem? We have the solution here, which is extrusion-based additive manufacturing. This process enables us to make mass customization through the kind of enabling technology, which is again PIM and MIM. We can use some kind of process steps and use a step which is called as deposition or 3D printing to enable mass customization as well as kind of shape scalability possible. Here you are saving considerably cost because you don't require any kind of tools or molds to process the powders or feedstock. So this is the kind of merit of EM process over PIM and MIM. So let's dive more into the EM process now. So we should require a machine which should scan in horizontal plane, but again, this is limited to the Cartesian kind of system. We will see other system as well. So the typical kind of controlling is happening in XY plane for this kind of system. Starting and stopping of the flow is important criteria for the machine to process this kind of material, because you need to stop at one end, then resume the printing from another end. Then the machine should also move in up or down. Either the machine, the bed or nozzle should move up and down to get the part 3D printed. Another process characteristics involve the material should, so like there is a one kind of limitation of some system which is reservoir, like there is a spool of filament or some kind of the kind of rods are there. So the machine, the part volume or the part shape is limited through the material which is present in the reservoir. But there is another system which is called as granule based system. We can see the commercial machines. You can feed the material continuously and you can make a bigger part possible. Then another characteristics required is the pressure, because you need to extrude the material. Again, I can see how I developed the system called as online rheology to measure the extrusion pressure on a real-time basis. So this is another characteristics of the material, of the process. The diameter of the nozzle is again important, because diameter and the extrusion speed, it ultimately result into the shear rate, and shear rate is important for the processing of semi-solid material, like it influences the viscosity of material. So that's why we need to consider the pressure requirement. The diameter is again important. As I said, it is up to the requirement, but the nozzle is important because the part which we want to manufacture is considered as an application wise, the resolution of the part, the accuracy of the printing. That's why the flow rate and other speed, that is also influenced by this diameter of the nozzle. The next criteria is about the material that is being extruded. Again, it is in semi-solid form. At the beginning, we should imagine that metals cannot be extruded. That's why we are using the PIM system. We are using polymers to get it in semi-solid form, and we can use it as an extrusion material. The material must be again in the that can be solidified, then which is deposited on the bed to retain the kind of shape stability. So there are two aspects. One is cold welding between two successive layers and the stability of the part itself on the print platform. So these two aspects are important for the stability of the material. So it should be extruded and get solidified as per the requirement characteristics of the application. The next characteristics is the temperature. When the material is in the form of molten form. So there are a few papers I published recently where the molten characteristics of the melt characteristics of the material inside the liquidifier or inside the reservoir is modeled through CFD analysis. and it is very much influenced by the kind of constituents of the material as well as the pressure that you are applying for extrusion. So the melt reservoir is also one of the criteria for this process. The next criteria is that kind of change of the phase during the solidification. So like we have some curing agent which is required for drying the part. By the way, there are, I'm not going into the much detail, but nowadays there are some system with the infrared cameras. If the material is getting solidified quickly without getting kind of the layer are not sticking, they use some heating system to make at a given temperature to stabilize the kind of part. Again, the approach is utilized for paste. Sometimes paste are applicable, sometimes granules are applicable, sometimes rods are applicable. So there are requirements, and it is not specified to the particular application. When it comes to the extrusion nozzle, which is again I said earlier, it's a resolution. Larger nozzle diameter enables us higher productivity, but reduced resolution enables us very high precision. So there are some system which can measure in real time with the CAD system whether it is deposited at a accurate shape or not, and then there is a feedback control. I will cover this aspect in some with my when I talk about my research work on this. Then again, so the deposited rod, when it comes to the deposited rod, it should not be the feature size should not be lesser than the diameter of the nozzle, because ultimately there is a kind of squeezing action is taking place between the nozzle and the platform. That's why you should consider the feature size in between the nozzle diameter and the extrusion volume of the material. Another aspect which is I need to cover is about the suitability of the large part and the wall thickness limitation. So there is a kind of thumb rule, I must say, at least twice the nominal diameter of the extrusion nozzle used. So this is typically if you go and look at the design rules for the extrusion system, you can have a lot many schematics where they are talking about the diameter of the nozzle, the diameter of the deposition stand, and their correlations. Again, the stability of the material, the cooling rate is another aspect that you should be aware of. Like it should be remain solidified, as well as it should not have any warpage kind of issues after deposition of another layers, because there is a heat which is coming from the newly deposited layer. It should not the kind of layers which are already deposited, the strands are already deposited beneath the new surface should not distort. That is a kind of requirement. So that's why sometimes there is a cooling fans introduced in the chamber itself, so they can cool down from the bottom, heat up from the top, so that it can maintain the kind of stability of the part as required. Some other aspect which is kind of gravity and surface tension is important when you consider cooling and drying process. Okay, so again, this part should not distort or damage because of the gravity and surface tension loading. Solidification and cooling will have its own impact, because the binder constituents, which is again in the polymer form, there is a phase change happening. So there is a dimensional changes because the liquid volume and solid volume of the binder is different, although metals are much stable because it's solid form. So we need to consider some kind of non-linear behavior in the designing of the part when you want very high accuracy of the parts need to be produced. When we consider the temperature and different chambers, you require a kind of surrounded atmosphere. As I said, the kind of system that you require kind of steady state condition or a kind of customized conditions, so that you can have operational requirements fulfilled for deposition as well as the stability of the part. Some other another aspects of the process, it is like plotting system that allows the movement of in the horizontal plane. Again, this is possible for Cartesian and some delta P printers. So we can see there are 5-axis planes as well. So it is this kind of term is not viable, but most common Cartesian system, it is very important that it allows in the horizontal plane. Then the coordinate like coordination of extrusion rate and the deposition is again important. Again, please refer back to some kind of modeling work which is related to the extrusion and deposition processes. By the way, there is another challenge nowadays people facing for the bioprinting, because again, it's a kind of some kind of another kind of complicated system involved in the extrusion, and there are a lot many complications in the deposition and extrusion. So there is a lot of scope in this kind of area of research. When it comes to the extrusion material, you should have maximum precision. It is again comes to the deposition as well as material side of the process. So you should have a very high accurate kind of positioning system with the movement of nozzle or bed, as well as there is should be some kind of overlap between the kind of infill and the periphery of the material, because it is important for the strength consideration. Okay, so this is a kind of typical characteristics that we need to consider while designing extrusion based system. When it comes to the stability of the part, you again require, so there is one kind of important aspect that you need to consider. Unlike other additive manufacturing processes, they believe that there is no need of support structure, but in EAM you inherently required a support. So you can see some kind of design aspects, like you can, if you have a kind of gradual kind of increment of the layers, you don't need any support. But if you have a kind of sharp change, you required support here. And you can have this kind of support manufactured through the same material or different materials. So you can see there are if there is only one nozzle in the system, you can go for similar material and then you can easily remove the support structure afterwards. Or you can have a secondary material. For example, some commercial machine have two nozzles. One nozzle is used for the primary material, which is actual part, and another material which is secondary part. So I will not go into the more detail what is the interface, how much is the kind of clearance you required, and all this aspect. But there are a lot many research is going on this aspect, and there are some commercial machines also available to cater this kind of challenge. When it comes to the scalability, as I said, it is depending upon the machine and the kind of structure that you are using. A general extrusion-based additive manufacturing process is very much scalable. If you change the material, for example, if you are using PLA, like for scaffold application, you can use in micron size, very small products using EAM process. When it comes to the another extreme end, you can see people are producing like big structure like houses using this technology, but again they are using concrete, not the metal and ceramics. Okay, so the process I want to say here is that the process is scalable. The only thing is you need to consider the productivity, increase the nozzle size, increase the flow rate, control the flow rate. The accuracy is different for different type of kind of materials. So when it comes to this kind of scalability, you require different kind of systems, right? The different kind of extrusion approaches. We can go for first approach, which is called as filament system, which is again similar to the polymer or 3D printer in general, what we call it 3D printer. We just use the same system. Let me check the time. Okay. We have some kind of filament system which are in place. Like after manufacturing of feedstock, you can extrude the filament, and in the form of spool you can store it and you can use it for the extrusion system. We can go for the plunger system. I can show you the plunger system that I used in my previous research. So you have a hopper, you put the material, and then the plunger pushes the material completely in a controlled manner. So the only issue with this, it is very high power material. You can use very high power to extrude the material, but the limitation is the size or the volume of the material. Here the limitation is, if your spool is finished, you will have you need to load the spool again of the filament. The limitation for this process is the kind of torque that you can achieve through this kind of motors. It is limited. Here you can have very high power and you can extrude any material easily. This system is more suitable for large parts, because you can feed the material continuously. You can rotate. It is a screw-based system. You can rotate the screw and you can deposit the material continuously, as long as you are continuously feeding the material. So that way each kind of approach is unique and is suitable for different applications and different requirements. We can see some kind of commercially available system for EAM process, metal extrusion with plunger system. Here you can see the studio system developed by Desktop Metal. Is again, the name of company is Desktop Metal, and their system is their machine name is called as Studio System. And they trademark this name called as bound metal deposition. It's the same process that we covered since last 1 hour. So they use a kind of plunger. So there are some rods. They manufacture a cylindrical rod. They put the rods in the machine. The rod is getting pushed, and you can getting deposited. The material is getting deposited. One of the competitor, Mark Forge 3D, again they develop the system called as Metal X system, which again utilize the similar concept of plunger to deposit the material in semi-solid form, and they call their system as atomic diffusion additive manufacturing, ADAM. It's the same extrusion based additive manufacturing of metals and ceramic. So again, to be honest, this process is very, very new, and these systems are launched in 2018. So you don't see any kind of commercially high productivity system developed for this kind of processes, but it is getting popular days by days. Another system which is utilizes filaments of the kind of feedstock. Filament system is long back Stratasys commercialized and trademarked their system for fuse deposition modeling for polymers. They are now introduced composite material, continuous fiber composite, metal matrix composite, then polymer matrix composite. There are in number of varieties they develop, but they are again using it for EAM. some similar systems for developing typically tools, fixtures, kind of for tooling applications. They develop a lot of systems. Like Stratasys, there are a number of companies. They develop their own products. You can see the list and you can compare the cost and pros and cons of their system. I'm not going to cover each and every machine manufacturer, but you can choose depending upon your application and your budget. So basically Stratasys is German rep kind of. So again, so this is a kind of open source system. You can build it your own, and you can utilize marker board system, 3D systems, and all these things. They are Ultimaker, again big player. Shareboard, Markforged, they are kind of very good machine manufacturer for regular 3D printers, but they are equally applicable for extrusion of metals and ceramic feedstocks. Another different type of category, which is screw. Again, when we consider screw, as I said, it is used for very large kind of parts or manufactured objects. AIM 3D is one of the German company, is one of the pioneer in this technology with the screw system. They develop screw system for various metals. You can see metal feedstock, ceramic feedstock, copper feedstock, tool steel feedstock. They develop lot of feedstock. Like I think they are commercialized them as well as, and you can use even catamold feedstock for their printers. There are another Delta printers available from Poland, AM, again American company, and like Cincinnati and Oak National Laboratory. They develop big area additive manufacturing system, BAAM. Like you can remember this by similar to WAM, wire arc additive manufacturing. It is big area additive manufacturing, which utilizes the material extrusion screw with the screw system. For metal as well as non-metallic constituent, like you can see a big chamber is used for deposition, and you can see how big XYZ Cartesians are there. There is a Delta printer is installed inside. So like very big metallic components can also be manufactured using this system. When it comes to the design, because we see the commercial system, but all commercial system are utilizing only 4 kind of machine designs in their system. One is very common, very popular Cartesian 3D printer, where you use this kind of system like X, Y, and Z motions constrained through the kind of rails and your extruder is fitted somewhere on a rail, and you can move it. It's similar to the polymer extrusion, polymer 3D printing machines. Then another is it is called as polar 3D printer, where you have like rotational and Z movement. Is here for the extruder. Rotational movement and y-axis is controlled through the bed only. So you have, I call it as bed and nozzle. So nozzle is only z-axis, and theta and y is on bed. Here everything is here you have 2-axis motion for nozzle and 1-axis motion for bed. The next system is called as Delta printer. You have all X, Y, Z controlled. So there is a fixed bed here, and the kind of Delta mechanism allows you to deposit the material over the bed. Again, the limitation is the size of the bed, because the Delta mechanism allows you to deposit from one end to another end, and it's very fast process. Another aspect is robot arm, similar to if you know direct energy deposition or kind of other processes, very big kind of deposition. We can utilize the robots to deposit the material in XYZ plane. Again, it is a very slow process, and lot many kind of kinematic links are there. Like accuracy is another problem. with this system as compared to the Delta printer. So here I want to summarize this kind of machine design aspects. You can see on this rows you have printing time, surface quality, and investment cost. And on columns, you have various printers, Cartesian, Polar, Delta, and robot system. I would like to, I must appreciate all the printers are very good for their own applications. But the application that I was targeting during my previous work, I selected this Delta printer because of its own merits. Typical is the printing time, because it's very fast process, and because the surface quality and investment cost is also kind of approximate or comparable to other processes. That's why I choose. But I used Delta printer, the Cartesian system, as well as robotic system to print the parts using EAM technology. So let's focus on this one. So I am going to cover some of my previous work now, which is a project called as FSTO. I performed this work in Politecnico di Milano during my postdoc work. It is the system called as extrusion of feedstock of metal feedstock for manufacturing of sintered tiny objects. So what we did, we developed a kind of machine which is capable of the commercial machines that you saw previous slide, they are capable of manufacturing in capable of moving the object or moving the bed in 3 axes XYZ. But we consider 2 more axes, rotational axis, so which makes us 5 axis. Parallel kinematic table was developed using this kind of system. We made the kind of unit. We used it a kind of commercial system we made it stationary, because we can easily feed. There is no need to move this kind of bulky, because it's very bulky. It's almost more than 20 kilograms of weight for this kind of system. So we want it to be stationary, and everything is moving. The bed is moving here, and the productivity is very high. There is you can rotate so that you can control the requirement of support structures, and there are other many more merits of these systems. So we predominantly worked on 4 aspects to develop this machine. One is machine design and development. So as I see, it's the prototype for this kind of application. We worked on process modeling and optimization of the EM process, because we started working on this process when there is no commercially or research work available. So we are one of the pioneer in this machine process modeling and optimization. Then we worked on considering Industry 4.0. We worked on process monitoring and control, how we can sense, how we can introduce the sensors, how we can introduce the closed loop system to control the system, and development of various different applications and different shapes and materials of the through this technology. So these are the 4 major categories I covered for this developments. So you can see the commercial powders are used for development of feedstock. By the way, the feedstock is developed in-house. So we use our own mixer, we use our own palletizer to manufacture the kind of raw material. So you can see the raw material for stainless steel is like this, like powders. And when we make it a feedstock, you can see binder is covered all over the powder, and it's very high, very good homogenized. Because I use this kind of study in the academic environment, so we went for more eco-friendly kind of binder system, PEG, PP, and stearic acid system. We used MBAB mold K83 water-soluble binder system, which is procured and mixed with the powder in-house. So we use this system. So during the studies, we used 6 different feedstock, 4 of metallic and 2 of ceramic. The metallic feedstock, again, diversity is there, like stainless steel, magnesium, again, challenging material for other manufacturing, other additive manufacturing, but it is very much viable and easy to manufacture using EM process. Copper is a very big challenge for laser based system because of the reflectivity. Copper and aluminum is a very challenging material to process using powder bed based processes. But it is very easily manufactured through EM process. Tool steel, again, not so challenging through powder bed process because of the good sinterability, but there are some toxicity involved in this process because of the elemental composition. But when you consider EM process, you are mixing it with the polymer, and these metallic constituents are not no more exposed to the environment, so it is very good to process using this technology. We are not going we didn't went for very exotic kind of application in ceramic domain. We consider very simple alumina and zirconia. Again, alumina is for structural application and zirconia for biomedical application. So we developed some dental applications through zirconia kind of materials. So this is the kind of machine that we used here. We have a control unit, PLC unit to control the machine. We have numerical control. We have data acquisition, data processing. Like as I said, we did a lot of instrumentation around this machine. Then extrusion system. Again, it is commercial extrusion system. You can see in the zoomed version, in the cross section, you can see there are some machine element inside the extrusion system itself. It is a bit complicated. I'm not going to cover the system, but this kind of spherical balls with some metallic balls, they ensures the polymer, like the feedstock is molten, homogenized even before the melting and extrusion itself. Although we mix it as a feedstock, but this system ensures that the material is very highly homogenized before extrusion. So that is one of the merit of this system, and you can get very homogeneous deposition through this kind of approach. So let me consider some of the research aspects that we consider. Like on the bottom, you can see if you want to dive into the more detailed studies, you can refer these papers. We can see that the shear rate, as I said earlier, it is not in the order of magnitude where we are using for metal injection molding. It is much lower. Okay, the extrusion domain. But again, this extrusion domain is not the real extrusion domain, but you can see it is 10 to the power 1 to 10 to the power 2, like 100, 10 to 100 per second shear rate we are employing for this extrusion. And we did some modeling for different extrusion pressure, because to simulate the process physically, there is a system called as capillary rheometer. We studied the extrusion behavior for different for understanding the melting behavior, extrusion behavior as a simulator, as well as in the machine itself. So like that's why we called it as online rheology. So we used some same system to measure the pressure and kind of approximate the melt condition during the 3D printing itself. And you can see that different like print setting and different kind of melt setting and nozzle setting enables you to have different characteristics of extruded rods. One is smooth and one is very like shears, what is called this? I don't remember the terminology. I think shark screen defect on this kind of extrusion. But in between, the extrusion pressure is different for each kind of rods, and you can have a compromise between the extrusion pressure and the quality of deposited rod. So we studied we did a lot of understanding on different feedstock, different kind of solid loadings, different kind of melt rheology, per considering the elongational viscosity, shear viscosity, elongational viscosity. Because of the time limitation, I am not going into much in depth. But I would like to highlight here that you have different, when we consider the flow activation energy, it is different for different feedstocks. Why? Because of the solid loading. You can see the flow activation is very earlier for the highly loaded feedstock, and when you have a lot of binder constituent, it is flow activation is much it's not so sharp, and you can get it at much kind of higher shear rates. This kind of information is important for us to design the extrusion parameters suitable for deposition. It is not so easy, but we did a lot of efforts to understand the physics of the process, and then the inferences are used to design the extrusion system. Then we distinguished the shear viscosity and elongational viscosity. Again, it is a unique study, because most of the studies in the elsewhere, they consider only shear viscosity. When you consider only shear viscosity from the rheometer, if you apply the same combination of understanding and the physics, you will not get part deposited as per your needs. So elongational viscosity is very important in these studies. Then we considered some kind of like process characteristics for understanding the deposition behavior. We consider a single strand deposition before jumping to the 3D printing. So you can see here the extruded 3D extruded wire of stainless steel. We consider as a benchmarking geometry. We used different solid loadings, different deposition conditions, like different nozzle diameter. You can see 600 microns, 900 microns. It's very tiny kind of deposition we achieved through our systems because of the merits of our extrusion head. So we understood that the deposition, so on y-axis you have diameter of extruded strand with respect to diameter of nozzle diameter, and it deviates significantly. I'm not going to discuss results here because of I need to dive into the more details, and it required a lot of time for me to illustrate everything. But you can see here the clear trend is that at higher nozzle diameter, the process is not so stable, but at lower diameter, the shear rate is much uniform at any solid loading, and you can get the same kind of distinction. By the way, when you consider 1, it is no swelling. 0.975 is so like it means that there is a different swelling ratios are employed to correct the deposition. Why we did all this study is to make sure that whatever is we are controlling on the computer is getting deposited, because there is expansion of the material because of the feedstock constituent polymers. The deposition is different. We need to design the rod diameter. We need to design the inter rod spacing. We need to design the layer height. All these parameters are the accuracy is possible through this kind of elemental studies that we have made. Again, here you can see extrusion velocity, VE, and table velocity, how they are influencing the characteristics of the here is the standard deviation in the diameter of the extruded wire. So it is different for different combination, and we studied lot of understanding through different combination of feedstock as well as extrusion temperature. Lot of combination of other variables are considered to make the process robust at an elemental level. Then, as I said earlier, we considered online rheology. You can see deposition of 316L powder, and very neat shape deposition is taking place here. Okay. So when you are depositing this one, we have a kind of mechatronic system connected to the extrusion system, and I can infer the extrusion pressure from the real-time deposition. So I will call it as so for each layer you can see how the extrusion pressure is varying. So at the beginning it is increased because of the stability of the extrusion flow, then it is getting stabilized. Like layer 2 and 3 it is more stable, layer 4 is the last layer, there is a stopping happening, so like that's why it is uneven. So this kind of information is used to consider the rheology of the material, because I'm measuring pressure, and pressure is inferred in terms of different categories. One is capillary pressure and die-entry pressure, which is differentiated, and the P total, again this is the theoretically modeled pressure, and this is P total is a actually measured pressure on the machine. So you can see there is some distinction, some trend is following. It is not following for all the time, for different diameter, different combination. It was discussed in this paper. You can, if you want, if you are interested, you can refer this paper to get more insight to these studies for different material, what is happening, how it is different, why there is a challenging approximation of this kind of material and this kind of pressure constituents. We went to further study this kind of characteristic for understanding the process stability of the part. So I believe that this kind of understanding is useful for determining the process stability domains. So you can see these red lines are determined for the best processing domain for this kind of material for given combination of parameters. Another aspect is stability. Again, this kind of thermal imaging is employed to monitor the real-time stability of the part during the deposition. You can see for different printing combination here, if you increase the temperature, your part stability is different. There is a distortion on the top side. If it is lower, then you have there is a cooling effect on the periphery, but there is a high temperature at the center of the core of the part. So it is again important to decide and fix the extrusion parameter, the deposition parameters. Again, it is again toward the smart manufacturing that we are working on. The next smart manufacturing approach is we did inline imaging. So like while depositing each and every layer, we took the pictures, and the pictures are on a real-time basis processed through a MATLAB code which is running on a computer, which can be used for identification of defects or the periods. I will not go into the more deep. So we realized this challenge because we understood that when we consider different surfaces of the part, they are distinct and the surface roughness is different. So how we can control these kind of characteristics on a real time? So we realized that challenge, and we started investigating this kind of concept. So you can refer my paper related to the deposition. So we considered some kind of variables index to understand the process stability, and the real-time kind of deposition correction measures can be realized through these kind of approaches. So you can see on the right side, the period identification was take place with respect to some fundamental parameters. We understood that when there is underfilling, overfilling, when there is a scratching of nozzle with the material, like overfilling nozzle interact with the depositor, if there is a lot of swelling of the powder deposited feedstock, there is a lower height of the print height, then you have issues. So we consider all the combination of the defects, and we realized two index, which is filling index and ununiformity index, and they are we did a lot of experiments to validate our model for different extrusion velocities, different combination of extrusion and table velocities, and this can be used for a kind of process criteria for real-time monitoring as well as control of the process. So we determine for the given combination of the deposition, this is the optimal combination. So once you are based on the image, if it deviates from this kind of numbers, there is a correction happening in the G code, and you can correct the deposition in the next layer. But honestly, it is not possible on the real time on the same layer, because we are taking images layer after another layer. Okay. We did some sintering and debinding exercises. You can see some sintered microstructure, some debinded and microstructure. We did some physical characteristics. Again, these data are available online, so you can refer to the what happens with the phase like weight change if you change the printing parameter, what happens with the volumetric shrinkage when you change the printing parameters. Again, this is the apparent one, but nowadays you know that there is another process called as X-ray microcity, which is used not a real time, but to understand what happens with the post-processing steps. So like we did the scans for ceramic, because you know ceramic inside ceramic it is very difficult to monitor or to approximate. So we did this microcity scanning. We do some image processing or just thresholding. Again, you can refer to this paper to understand how the porosities evolved through these process steps. Then we did some kind of numerical modeling to validate porosity, sphericity, and diameter of pore through this kind of process steps. And I would like to compare here the green and sintered condition. You can see through microcity, you can visualize the kind of porosity throughout the part. We did a lot of efforts to extract the sample, like thousands of the images to extract it in z axis in the build plane to determine the porosity level, sphericity. Sphericity means how the particle, the pore look like, and how the shape is, and this kind of characteristics is studied and compared with the process steps. You can see here it is more homogenized. The diameter and the pore is not so dispersed here. So these are the kind of outcomes we observed through this study. So some of the studies are resulted to the development of products at a prototype level. You can see some diversity of shapes and materials are processed in the lab scale again. So that's it from my research related to EAM. I would like to summarize here by comparing the powder bed processes and extrusion processes. You can see particle requirement is much finer. Material or any material is processed. Any kind of so cost is very low as compared to the commercial powder bed process, because they are laser system, powder bed, and all these things. There are a lot of other costs are involved. Energy is low. There is a need for inert gas for metal processing, air for ceramic processing, because ceramic is a stable material as compared to metals. So there are other aspects I compared here: speed, post processing, like maintenance cost, and other costs. The major limitation of extrusion based process is the multi-stage process, because you have debinding, thermal debinding, solvent debinding, sintering step, which is taking place after the 3D printing, right? So that is a major bottleneck. But this process can be the parts can be processed in a bulk or in a batch size, so which increase the process competitiveness as compared to the other AM processes. That's why we like the commercial players and other academians refer this process as very cost effective as compared to the powder bed based processes. So it is almost 10 times lower than the cost of SLM and EBM processes. So this is the last slide from my presentation. I would like to summarize here with the process description. It required nozzle and orifice to deposit the material. Any material, any form can be processed, but it should be available in the pellets or filaments. There are certain merits of the process. There are certain weaknesses of the process. We already discussed these merits and demerits of the process, so they are listed just here for your reference. I would like to highlight here as the first the commercial system for this process is available in late 2017, and I used desktop metal printer in 2018. So there is a lot of things to happen in this domain. Okay, like currently the cost effectiveness of the machine building is possible. Powder cost is need to be reduced, but it is also equally applicable for other AM processes. New materials are coming. They need to be optimized. Applications are coming. Then we should go for considering the sustainability like all over the world, and there is a need for developing the methodology for zero defect, how you can correct the part characteristics on a real time. There you come digitization of process, like lot many sensors, lot many meta models, algorithms, actuations, digital twins, all these are coming into picture to make it possible for the coming era of mass customization and net zero manufacturing. Thank you. Now I can, if we have some time, we can consider some questions.
Thank you, Dr. Kedar, for wonderful session. So, any questions from the participants? Please feel free to ask. Yes, participants, please feel free to ask the questions. You may type the question in the chat box also.
So I think our audience is not yet kind of confirmed that the processes really have some potential, or is there any kind of, I think that the process is a bit kind of multi-step. Okay, so many of you may not appreciate the kind of merits of the process, but it is really kind of eye-catching for many of the industries, to be honest.
Yeah, definitely.
So we are aware about like laser based processes and other like direct energy deposition processes. But again, if you want to like discuss about those aspects as well, I'm open, because I work on other processes as well. Okay, so like if you want to compare it.
Yes, please participant, discuss if you have any doubts.
So, participant, please at least comment in the chat box that the session is clear, and I delivered the kind of required information to know you better on this kind of technology. Okay. Or if you have any kind of suggestions for further improvements of this process, if you know something, or if you see that the process is not competent with other additive manufacturing process, we can discuss even through chat.
There are few compliments received from the participants. Dr. Rupendra Nete is saying nice informative session on new process. Okay, so yeah, it is really a tremendous potential in the process is having. Ravi Kumar is saying like very informative session. So but few compliments have come furthermore on good
Yes.
informative session and presentation is good.
Mhm.
Dr.
Yes.
Kedar, I would like to request one more thing is if you can share your this presentation that will be helpful for the
Sure.
participants to
Sure.
for the study material and
Mhm.
for reference purpose.
Sure.
Okay, so I thank you once again for this wonderful session and
Mhm.
informative session. I request participant maybe Smita to give the vote of thanks.
Yes, sir. Good afternoon to one and all present here. It's my privilege to present vote of thanks for today's session. I am very much thankful to Dr. Kedarnath Rane for giving deep insights of the topic extrusion-based additive manufacturing processes. Thank you so much, sir, for spending your valuable time from your busy schedule for this FDP session. In this session, you have very well explained the basic aspects of additive manufacturing processes. You have nicely explained the extrusion additive manufacturing for metals and ceramics. You have explained the basics of MIM and PIM process with the help of visual case study. You have briefly explained PIM process capabilities and materials processed by PIM. Then you have covered the topics metal powders, manufacturing of powders, and powder for MIM and PIM. You have covered the topic ideal powder characteristics, binder, feedstock and its properties, molding, debinding process, and sintering process. You have also covered the topic EAM process over PIM process, supports in EAM process. Then you have explained the material extrusion approaches with plunger, also with filaments and screws, which are introduced in latest years like 2018. We are very much thankful for sharing your knowledge and experience with us, sir. Thank you so much, sir, for such an informative session. I am thankful to Dr. Kiran Bhore, Dean R&D SPCE, for organizing this FDP. Last but not the least, I am thankful to all the participants for your time and attention. On this note, I would like to say end of this session. Thank you one and all.
Thank you. So I declare the closure of this particular second session. So we will have a lunch, and after lunch we will meet at 2:15 for the next session or the last session of this particular day. Thank you very much. Thank you, Dr. Kedar, once again.
Thank you, sir. Thank you for
Thank you.
giving me opportunity and see you next time. Bye. Thank
Yeah,
you.
bye bye. So the feedback link has come. You can give your feedback through the feedback link. Thank you very much.